Hello, everyone. We'll start the session in just few minutes, but before that, I would like every one of you to fill the pre-session form that we have sent in the chat box and also download the Google Colab link that we have given to you and open in Google Colab. That would help us to make the things move faster. Once every one of you have filled the pre-session form, please react with a thumbs up. That would help us to start it very earlier. I'm just waiting for you all to fill the pre-session form so that we can start fast. Please let me know once you have filled the pre-session form, because that will help me to understand how to get it better for you in the whole session, to understand what do you need in the session too. And you all can switch on your camera also, please. That would be very well. Um, Arav, the pre-session form is in the chat box itself. I'll share it for you once again. Did you get it now? Is everyone able to see the pre-session form? If not, please let me know so that we can start it faster. Who all have submitted? Can I know that? Okay, thank you, Han. Are you all excited for the session today? If you're excited, react in the with the react button, please. Let me see how excited you guys are. Hmm, great. Okay, who all are left to submit the pre-session form? Can I know? Is it taking a long time? I guess it's only 2 minutes. Okay. Okay, we'll just start it now. Great. Let me know if you're able to see my screen. Uh, I want all of you to see this video first and just see it for some time, and then we'll start with our actual session. The audio not audible to everyone? Okay. So did we see? I'll see the video now. How was it? It was 549,000 kilogram of a rocket that left the ground there. So that is roughly a weight of 75 adult elephants stacked on a launch pad. And someone said, yeah, let's light this thing on fire and we'll point it at space. That's how a rocket, that's big, how big a rocket is now. So I just want you all to answer one question for me. What force do you think made this thing happen? What force made the rocket move up? Can you all tell me? Just one word, not much. Okay, I can see people answering. Okay, I can see few answers in the chat box also. Drag, thrust. Okay, aerodynamics. Nice. Okay, we'll end the poll now. We'll see the answers over here too. Okay, so no one said air. Everyone said thrust. Everyone said fuel. Some said aerodynamics. No one said air. Did anyone say it? No. So good that no one said it, because if any one of us is thinking that a rocket is pushing against the air the way a fan pushes air, that's completely wrong. So it is not air at all, because rocket is pushing against their own exhaust, like the exhaust gas screaming downward at 2,886 meters per second. That is Mach 8. Now, and Newton says that equal and opposite reaction happens and the rocket goes up. So no air is needed, because the place that we are sending our telescopes or payloads or any rovers which is going into the space, there is absolutely zero air, because space has vacuum. Now, here is the real question for us today. And it is not really about rockets, because it's not about how rockets, it's basically about how rockets are going and why they are going. Okay. So for that, we'll basically going to discover why Earth's atmosphere hides most of the universe. Then we'll see about physics of the telescope. We'll talk about Newton's law and simulate the forces. Now, every astronomer in the world lost their sleep over one question. How do we get our scientific instruments above the Earth's atmosphere? Now, not because going to space is cool. It is cool. It is extremely cool, because every one of us always wanted to be an astronaut for sure, because we all wanted to go to space. Is it not? Yeah. So, but because Earth's atmosphere is the very thing keeping us alive right now, it is also making it scientifically completely blind. That is, think you are watching a whole movie, but someone put a massive filter in front of it that makes the screen block 90% of the visibility. And now you can only see a thin sliver of the full picture. You cannot see the full picture, but you can see something blurry going behind that. That is literally what Earth's atmosphere is doing to the universe, because we are not able to see everything. What all we want, we are not able to see that. So, what do we do for that? Now, Earth's atmosphere keeps us alive. We know about it. But visible light is the only thin band of light that we can see, which passes through the Earth's atmosphere. And because of that, the ground telescopes are working. But it's a very narrow window over there. And ultraviolet, it is blocked by ozone layer. Hot young stars that are forming right now, or the stellar nurseries that is happening, it's completely invisible from the ground. And then we have X-rays also. It is also blocked entirely. See, the black holes are actively feeding over there. Neutron stars are zipping around 700 times per second. And it is totally hidden from us. We all want to see that. We want to know what stars are doing, what the galaxies are doing, and what life is beyond the Earth. So, and infrared also. It is mostly blocked by water vapor itself. And dust clouds where planets are forming are among other stars. We literally cannot see anything from here. So, can you type an answer? What is the obvious solution to this problem? What is the obvious solution to this problem that we are not able to see everything from the Earth's point? Can everyone answer the poll? I'm waiting. Let's do fastest finger. Fast, 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 fast. Okay, one person answered. I'm still waiting for the others. Yeah. Okay. Let's see what are the answers. Okay. So I'm not able to see any of your answers. Where is your answer? Okay. So yeah, I can see someone answered that launching a telescope directly above the atmosphere. Exactly that. Like Hubble, Chandra, JWST, all of these big telescopes that we have heard about, every single one of those observatory exists right now because of one problem. And rocket is not the point. Getting above the atmosphere is the point over here. So now we want to understand why. Do you see this image over here? Just look at it for 1 second. Yeah. So December 1995, astronomers pointed Hubble at a patch of sky that looked completely empty through every ground-based telescope. So whenever they were looking through ground-based telescope, everything was empty. So their colleague said, you are wasting the telescope's time on nothing. Don't use 10 telescopes at a time on one single patch of the sky. But they still exposed it for 10 days. And what happened? They saw 3,000 galaxies, more than 3,000 galaxies, and each one contained hundreds and billions of stars over them. So, light from some of them had been traveling for more than 10 billion years to reach the detector. 10 billion years. How does that make you all feel? Can you just tell me? Does it make you excited to know more about the telescopes and all? You can also share in chat. Yeah, great. So, because it's It is very exciting because none of it was visible from the ground. None of it. Now, a single decision to launch a telescope above the atmosphere produced this particular image. That is why we do launch mechanics. That is our today's session. And not for the rocket, for this, the end result that we get after we launch a rocket. And so all of you did get this Google Colab notebook in the chat, right? Did we get it? Did we download it? Good, Zaim. I can see that you downloaded it. Did we all open it in Google Notebook too? Great. Great, Ishita. Great, Ismail. So now, before we go to that notebook, let's see why we need it. So, in 1903, this Russian school teacher named Tsiolkovsky derived this equation that governed the rocketry. So we want to get a telescope above the atmosphere, how hard it can be, right? That might be the famous last word. So Falcon 9 is a famous SpaceX rocket we all know about, right? So it weighs 549,000 kilogram at liftoff. Its payload to orbit, okay, and the actual thing it delivers is only 22,800 kilogram. That is only 4% of its actual weight. It was 549,000 kilogram when it was on the launch pad, and when it reached and delivered the payload, it was only 22,800 kilogram. That is only 4% of the total weight. Now imagine you order a pizza and the delivery person is showing up with a big truck weighing 2 tons, but your pizza only weighs 1 kg. It is roughly the mass ratio that we are dealing with in rockets. So, like a quick math question that I want you all to do, and give me the answer on the chat box. Okay. If 75% of the rocket is fuel, what percentage is everything else? That is the engine, the structure, the telescope, all of it. Type it in the chat box. I'm waiting. If 75% is the rocket fuel, then what is the rest of the weight? What amount is it? 25%, right, Shreya? Great. So of which the actual telescope might be only 4% of the total mass. Everything else is the cost of fighting gravity. Now, the Russian school teacher, Konstantin Tsiolkovsky, figured out exactly why. Before aircraft existed, before anyone had built a working rocket, he sat down with a pen and paper and derived one equation. This, which says delta V equals VE times natural log of M0 over MF. Okay, now let me translate this into simple English for every one of you. This looks like a big one, but we can translate it easily. So delta V is how fast you can go, and V is how fast your exhaust exits the engine, the gases that exit the engine. Yeah, and the most important engineering number in rocketry is VE. And the logarithm in the middle is the villain of the whole story. Complete villain. Now, because the logarithm exists, it means that when you double your fuel, you do not double your speed. Okay, I'll explain you how. So you're trying to run faster in a marathon. You eat one energy bar, great. You feel better, you run very fast. Then you feel that I want more energy. You eat one more. But does that mean if you eat 10 energy bars, will you run faster? No, right? You might feel sick and you might not able to run also. So every extra kilogram of fuel that we are giving is less additional speed over there. So this equation is exactly why JWST has 6.5 meters of primary mirror and not 10, because we can only launch what fuel budget mathematically allows. And Tsiolkovsky draw the ceiling in 1903 itself, so that not more than 6.5 meters was allowed now. Now that is the cost of getting there. So how do engineers cheat this logarithm now? How would you beat diminishing result like this? Can you guess it? Like what are engineers doing that is diminishing the result, but they're able to go higher also and at higher speed also. What is it? You can type in chat box also. Changing the rocket shape to make it sharper and more rapid. That would increase the speed, yes. But what else? Reduce the weight of rocket, increase the. That's what I'm saying. You cannot increase the amount of fuel. If you increase the amount of fuel, it might go more slow because the weight increases. Have you all heard about staging? Rocket has multiple stages, two-stage rocket, three-stage rocket. Have you heard about it? No? Okay, we'll see about it today, okay? So now imagine you're running a marathon again, and you're carrying a very big backpack with water bottles inside so that you can drink water while you're running. Now, as every bottle finishes, will you just keep the bottle in your bag and carry the weight? No, right? You will throw the bottle and you'll throw the bag also by the end of it so that you can run faster. This is what happens. So, whatever empty weight or whatever fuel tank is empty, we'll throw that away and it reaches back to Earth. And the only thing that left behind, the payload or anything else that we want to take higher, that's the only thing that we're carrying. So that improves the whole math dramatically. So, and Falcon 9 does exactly that. But with entire engines and fuel tanks is left behind and it takes only the payload. That is the 4% of the weight. So now the moment the the moment stage one runs out of fuel at 66-kilometer altitude, the entire stage one engine tank structure separates and it falls back on the earth. It's cool, right? And then the stage two will continue further with a completely fresh mass ratio. And logarithm is again in your favor and it's not the villain now. So we need to use our brain sometimes. Now, I'll try to show you how that happens. So we'll share something else. Okay.
You've heard the call out. Vehicle is supersonic. Side boosters are now throttling back up to full
Vehicle has
power.
reached maximum dynamic pressure.
We're past max Q, the period of maximum loads on the vehicle. Next up, we'll be waiting for the side boosters to begin to throttle down prior to booster engine cutoff and separation 2.5 minutes into flight. GNC trajectory looks good on the Falcon Heavy. Reports show that the M1D engine performance is nominal.
Exact engine says
Major event coming up with side booster shutdown and separation.
inside shutdown. Side boosters. Beaker. Center. We just them up.
Did you all see how that separated out? Yeah. Was it cool? Yeah, great. So we'll come back to our stuff back again. Can you see the screen again? The PPT? No? Uh-oh. Okay, great. So now this happened at t plus 162 seconds. That is after launching. 162 seconds later, 66-kilometer up in near silence. Two stages separated. So stage two is continuing alone now. That movement has a name that is called MECO, main engine cutoff. You could have seen that in the video also. It was written as main engine cutoff. And we'll also see that in our simulation that we'll be doing so. Okay. Now we'll see the main hero, the actual force behind all of this. That is how simplest possible version of how rockets work. Stuff goes out in one direction, other stuff goes out in the opposite direction. That means Newton's law, Newton's third law. Okay, that exhaust fuel goes down at extreme speed and rocket goes up. No air required. It also works in vacuum. So, more precisely, the combustion on the engine creates the hot exhaust gas, and that exits the nozzle at 2,886 meters per second. That ejecting the mass downward gives the rocket upward momentum. That is the Newton's third law. And the beautiful part, no air is needed. So whoever was saying air at the starting question is wrong. Rocket is pushing against its own exhaust, own fuel that is coming out. This is why it works in the complete vacuum of space where there is literally nothing else to push against. That means, have you ever used a balloon? You blew up that balloon and after that you just left it. Did it just go here and there? Have you all noticed that? No? Yeah, I can see few people saying yes. Okay. Now we have three terms: max Q, MECO, and SECO. Every launch broadcast uses them. So now, if anytime you are seeing a rocket launch, just make sure of these three words, these three terms: max Q, MECO, and SECO. Very easy, right? So max Q is T plus 72 second. That happens at 11 kilometer. Okay, that is, and then we have maximum dynamic pressure. Okay, and the rocket is moving fast, but still relatively thick air. The force of the air is still pushing against the vehicle. Now, and SpaceX actually throttles the engine down at the max Q. And not because they lack power here, because the structure cannot handle the full engine thrust and the maximum aerodynamic pressure at the same time. And the rocket would tear itself apart. So now imagine you're driving a car at a full speed at a speed bump. What could happen? You could floor it technically if you have the power. But if you go off slightly, because you know exactly what happens if you do not, right? The speed bump here is the atmosphere, not the speed bump that we have on the road. So now, does that make sense to everyone? Yes? Can I get a thumbs up? Yeah, great. Now, MECO. Can you see that MECO? MECO is at T plus 162 seconds. That is 66 kilometers more higher. That is called main engine cutoff. The part that we saw right now saying the first engine got off and the other part was going up. Okay, so in the Falcon 9, only all 9 Merlin engines off, explosive bolts fire, and the stage is separate, and the stage 2 single Merlin vacuum ignites up. And here is something really satisfying that happens at exactly this moment. Drag drops to near zero instantly because at 66 kilometers, there's essentially no air left. And from MECO onwards, only two forces matter: gravity and stage 2 thrust. Okay, this physics simplifies completely. Now, SECO. SECO is at 570 seconds later. That is at 400 kilometer when we have achieved the orbit. Okay, now we'll go back to the notebook that I shared earlier. Can you all open the notebook and let me know if it is opening correctly for everyone? Okay, you have opened in VS Code. Okay, Han. I shared it. Yeah, I can share it again for sure. Just a minute. Can everyone see the notebook again? Did everyone get the student notebook? Can you open it and open it in Google Colab? Very good. Once everyone has opened it, please let me know. Does everyone have something like this with them? This is not the same one that you're having, but yeah, it's different. It's mine. You guys have got yours. So please open that. Yeah. Can you see the student final code? Did you all have it? Do you all have it, please? Let me know. Can you all react? I can only see Zaim reacting. Ahan, Shriya. This huge chunk of code, I'll explain to you, Zaim. Don't worry. You don't have to do everything, okay? I know it's very huge, but you'll get it with yourself so that you can read it at your own time and understand it. But right now, I'll explain you what to do and you'll get your results. Okay? Fun? Okay. So, uh, each of the cells you'll have to run in order only. You can either click the play button or you can do shift plus enter. Okay. And everything should be done together. You have to code here at cell 3, 4, and 5. That is checkpoint 2, 3, and 4A. You'll have to fill in some blanks over there. I'll tell you what has to be done. Okay. Okay. So we'll start with cell 1A. Shall we start it? Great. So, can you all run the cell 1A? If you are getting this, please run anyways. So this will load NumPy for maths, Matplotlib for charts, and IPy widgets for the live sliders that we'll be using in checkpoints 2 and 3. Just run it simply. Okay, is it done? Everyone run it? Can we go ahead? Okay, can we run the cell 1B now? The next cell, cell 1B, it is just color code for the dark theme so that it looks like space. We'll run it and then we'll move on. If you guys are having any issues, please let me know. If you're not able to run it, if you're getting any errors, please let me know so that we can fix it. I don't want any of you to be stuck in the code with that huge chunk of code that Zaim is scared of right now. Are you guys scared of that code? Okay, did everyone run cell 1B, the color palette code? Did it, what does it say? What is the result telling you down? Did it say colors and style helpers are ready? Great. Now we'll go to cell 1C. Before we start there, I want you all to do a quick maths. For 411,000 divided by 549,054, what percentage it is? Type it. I'll share that in the chat also so that you can. Can you all type it first? Let's see who's fastest in maths. I want to know. Fast, fast, fast. I have no idea. Okay. It's 75%. 3/4 of this rocket is fuel. The telescope is roughly 4%. Everything else is the cost of fighting gravity, as we discussed. Now here you can see few numbers. Okay, see, Ishita said it is 74.86%, roughly 75%. Correct, Ishita. So here you can see some physical constant, that is G, radius of Earth, rho naught, that is the air density at sea level, and atmosphere scale height. And we also have few numbers like VE, which says 2,886 meters per second, that is the exhaust velocity of the Merlin engine. And this number is going to multiply the entire Solkovsky equation that we saw, and we will be seeing in about 5 minutes. And the most important number today also. So M total here equals 549,054 kilograms, and the M propellant, that is the weight of the fuel only, is 411,000. Okay. So these are the numbers that we need to know. Can we all run this, please? Great. Did we all run it? Did we get all these physical constants loaded? Falcon 9 parameters are loaded. And orbital velocity, that is the lower Earth orbit, we got it. Done? Great, Ismail. Okay, Shashvi is also done. Okay, now we'll go to the next cell, 1D. That is the simulator. Now, this is the engine for our simulation. This is the engine behind every chart and animation that we're going to find today. It runs a loop every 0.5 seconds from liftoff to the orbit when it reaches, and each step it calculates three forces and updates the velocity and position. Now, you can read the comments also over here that will explain you everything. So even if you are trying to do this code later at point of time, you'll always have this to explain it to you. Every line will make sense today by the end of the day. So if anyone has a collab error, please let me know. And please run this code too. Did we run it? What is that we are getting over here? Okay, we have gotten that simulator is defined and it's run. We have got 1151 steps. We have got peak altitude. We have got peak velocity. We have already got the orbit target also. All setup is complete. Now we can go to the checkpoint one. That is the orbital speed problem. Okay. Now, at the checkpoint one, the question we are answering right now, why does carrying orbit cost so much? Okay, can we just run this cell too? What are we getting? See, why is reaching space so hard? Okay, space is starting at 100-kilometer altitude. Okay, and London to Paris is 340 kilometer. You could drive to space in an hour basically. The real challenge here is the speed. You need to have that particular speed. To orbit at 400 kilometer, you must be traveling sideways, not straight, sideways at 7.67 kilometers. And that is what the orbit means, not just going out. So to reach lower Earth orbit, we need this speed. And a rifle bullet is only having this much speed, and a walking only has this much speed. You can see everything. This is the checkpoint one that we are having. Now, let's go to the next. This is the main star for today. We already saw this equation, that is delta V equals to VE multiplied by log of MI over MF. And VE is the exhaust velocity, MI is the initial wet mass, that is fully fueled mass, that is the total mass with the fuel. And then we have the dry mass. Dry mass is minus the propellant, that is fuel. And then we have the natural logarithm. Okay. Now here, you will have to fill in the blanks over there. Can you guys see the blanks down? See, at MI, you are having a blank. Can you remove the blank and write F9 equals to F9 in the square bracket M total? I'll give it to you in the chat box also so that it is easy for you guys. Did we get it? It's already with you also, so you can just use that too. Done? You can just copy on the one that is on the side and you can use that. We should use the double quote, not the single quote, please. Done? And now we'll go to MF. That is the final mass. That should be the total mass minus all the propellant. So we'll subtract the F9 double quote M prop. F9 square bracket double quote M underscore prop. Small m. You can just copy paste. That would be better for you guys. It would be easy also. Prop, P-R-O-P, prop. Done. So now next we're having R. R is Mi over Mf. So we'll write Mi and Mf and Mf. Now we'll fill in our Solkowski's equation, that is dV would be having VE into math.log R that we just saw as Mi over Mf. Are you able to do it? Is anyone having any doubt over here? R. Capital R, madam. Yeah. So now did we get the equation as dV equals to VE multiplied by math.log R divided by 1000? So here what we saw is Mi, that is the initial mass, is F9 M total, that is 549,054 kilograms. The entire rocket fully loaded, sitting in the launch pad, ready to go. Done. Now, MF we are having, that is the final dry mass. That is the one where almost everyone would have made the first mistake. If I did not tell you, if MF is not the propellant's mass, it is what is left after the propellant has burnt. That is the dry rocket. Just like if you're having a water bottle and I asked you 1 kilogram of water bottle and there's inside the water is 750 grams, the empty water bottle will be weighing what? 250 grams, right? That's it. So now MF equals M total minus M prop. We did that. Everything is done. Now R is also done as Mi over Mf. dV is VE times math.log of R divided by 1000. We divided it by 1000 to convert meter per second to kilometer per second. Okay. And the critical mistake, if anyone is knowing about, who is stuck? Like in cell, the which line of code the blank is. Are you not able to see Zain? Can you unmute, please, and tell me no?
Uh, yeah. In the cell tree, where's the blank exactly?
Where the blank is exactly? Okay, I'll tell you. Did you go to the checkpoint 2, which says Solkowski equation?
Right here.
Yeah. And does it say fill in the blanks, 4 blanks marked in cell 3?
Yeah.
Okay. Yeah. Now, when you go down, you can see like 4 blanks over here. That is the step 1, step 2, step 3, and step 4. Was it visible now?
Uh, yeah.
Okay.
So,
Now can you do it?
can I share my screen so I can properly show you?
Sure. Were everyone able to do it other than Zain?
So, here we should fill in the line of code.
Yes. Here you have to. So you did V equals to F9 V, right? Now MI. Okay.
Where, um,
Can you share the code only, sir? Yeah. Now, Mi, that is our initial mass. You can, what are you doing? Go back. So the next
Uh,
step two. No, step one is done. You don't have to do anything over
yeah,
there.
yeah.
Okay, you just can you remove whatever did you did right now? VE is supposed to be only F9 VE. That's it. F9, capital
Uh,
F9.
F9.
Square bracket.
Where's
I'll
I mean,
uh,
sorry.
I'll I'll give it to you in the chat box. Can you just copy it for me? Okay.
F9 B.
It will
Uh,
Now you need to type in the step 2, that is Mi equals F9 M total. That also has given to you in the chat box. That also is available to you on the right hand side where hashtag fill in is given to you so that it's easy for you. You can copy and paste that also. Can you see that?
Step 2, I should copy and paste this.
The Mi equals, there's a blank, right? Remove the blank and you can fill F9 M total.
Oh,
Okay?
yep.
And in the next line, you will have to do F9M propellant. That is the propellant mass we are subtracting from the total mass.
Uh,
Can you see on the screen how it is written?
it's written F9M underscore total.
Yeah, that's done.
Yep.
Yeah. So now step 3, we'll be talking about the final mass. The final
Mm.
mass is F9M total minus F9M prop. Is it done?
A sec.
And next we are having step
Yes.
4. Now the step 4 will be mass ratio. That is, we have to write Mi over Mf. So you'll have to remove R equals the blank that is there, remove the blanks, and you can write as Mi over Mf, just like how it is shown on the screen. Can you see? It is highlighted also for you now.
Yep.
Great. Now, can we go to the step 5 where you will having two blanks. One is after dV equals a blank. That blank is supposed to be VE. VE. Fill in VE over there. Remove the blank and we'll fill VE. It should look like how we are seeing it on the screen.
Step 5.
Yeah. dV equals to
Yes.
VE. And then you can also see a blank in the bracket. So remove the blank in the bracket and write capital R over there. That is our mass ratio. Is it done, Zain?
I think so.
Okay. Can you show your screen to me so that I can see if it is actually done and it's not how you think? Okay. Uh, okay. You did not write VE after DV.
What?
DV equals that blank, remove it and write VE. Yeah,
Capital.
VE. Small, 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 small. Yeah, that one. Done? Can you
Yep.
all run it now, please?
Sorry.
Can you all run
Uh,
the cell now?
what? I can't hear you.
Can you run the cell, Zaim?
Oh yeah.
Yeah, you can stop sharing your screen also. What did we get? Can we see that now? Oh my God. Can we see the left chart only right now? The left chart that we can see. Can you see how the curve is flattening as the mass ratio is increasing? That is what the logarithm does. It is doing its thing over there. That is more fuel, less return per kilogram. So the curve goes vertical rather than going vertical, it keeps flattening over there. This flattening was the reason that we did not send the primary mirror of the JWST telescope as 10 meter and sent it as 6.5 meters. This curve set the ceiling and Tsiolkovsky set the ceiling in 1903. Now, we'll go for the checkpoint 2. Yeah. Yeah, the next checkpoint can we go? And we'll run that. We have two blanks over there. Can you
Wait,
see the two? Right? We
wait,
have
wait,
two.
wait.
Okay,
It's
Zain.
showing me error.
Shows error for you. Is
Yep,
anyone else
and
having any error?
error traced back most recent cell.
Can you show me what's happening in your screen, please?
See, error.
Okay, can you go to the VE step? Yeah.
Yeah.
Okay. You have written F9 twice over there. Can you just remove
Oh,
it? Yeah,
remove the
F9 should
first
be
one.
outside the bracket, not inside the square bracket.
So I should remove the
Yeah.
second. It's not letting me type. It's not letting me type.
It would let you type Zaim. Or you can just click on the green part that is shown below.
Yeah.
Yeah, can you click on
Click
that?
this.
Yeah, so that is working,
Click
right?
this.
You can remove the red one. That would be easy for you.
This one.
You reverted to the change. Now you can edit it now. You can just remove the
Yeah.
F9 that is inside the bracket and the bracket, extra bracket also. Inside the bracket, not the outside one. Inside the bracket. Uh,
So right here,
yeah. Yeah, do
I
it.
should remove the yellow brackets.
Yeah, can you remove that yellow bracket also, please? And now you'll have a red bracket at the start. Yeah, that's it. Now you can run it. Great.
Yeah, it works.
Great. Okay.
Yep.
Now we are having checkpoint 3. That is, we are going to design our rocket. And we have two sliders that we have to use. So we'll have to two blanks also that is supposed to be filled. Okay. Can we go down and see where our blanks are? You're having it after update 4. And we can see it as fill in delta V using Tsiolkovsky. Can you all see it? If you can see it, please react with a thumbs up. We are doing very important part over here now. Yes, I can see everyone can see it. Uh, so here we'll be filling in just what is shown as the arrow mark down there. So we'll fill it as VE4. Can we all fill it as VE4? Okay, the next block, that is the next blank that is over there, that has to be filled as 1. 1 minus FF4. You can see the formula up also. You can see that what it should be. It should be 1 minus FF4. Yeah. Is it done? Did everyone do it? Just like how it is shown? Now, so here delta V from the fuel fraction, that is FF4, is V times the natural log of 1 divided by 1 minus the fuel fraction. And that all is divided by 1000. So fuel fraction is 75%, that we have already discussed multiple times in the lecture today. Okay. And now we go to the blank 2, that is the thrust to weight ratio. Can you see TWR equals to F9 in double quotes thrust underscore SL? Yeah, there we'll be writing as THR4. THR4. Now TWR is thrust divided by the total mass times G. Now here we'll be writing total. We said TWR is thrust divided by total mass times G. So we'll be writing total into capital G. Capital G we defined earlier as the gravitational constant. Okay, done. Now what happens? Okay, hi Zain.
Something's happening in my line of code.
Someone is editing your line of code?
No, not like that. I'll show you. So can I show it to you?
Yeah, sure, please.
Okay.
What happened? Can you go down? Yes, yes, yes. Yeah, you did not type it, no, Baba? Can you type it, please?
We're right here.
Yeah, see, the arrow marks are
What should
given.
I
You need
type?
to type all of that. You also did not type FF4, I guess, on the top. 1 minus FF4 has to be done in the first fill in the blanks. The first one. No, not that, not that. There only. Yeah, here dV4 equals to VE4 into math
Oh,
log, you
yeah,
did?
yeah, yeah.
Yeah, 1
Yeah.
minus 1 minus FF4.
1 minus this is 4. Here,
Inside the bracket, please.
set the bracket.
Yeah, FF4. The
I
one
should
that is
write in capital
1 minus, please.
1
1.
minus
F.
SF4.
Yeah, double F4. That is your fuel fraction.
Yeah.
F4. Capital Allah, small f. After minus
Okay.
sign, the 1 minus FF4. Your minus is after FF4.
Uh, right here.
Yeah, great. Now next part that you're having TWR written. Can you see that? TWR equals to F9. There only, just below that.
Yeah.
Yeah,
Yeah.
here you'll write THR4.
Right here.
Yeah, THR4. No,
THR.
in the first blank, in the first blank, Zain. THR4.
THR4.
Okay, remove the
Yep.
blank also, please. Otherwise, you'll get an
Oh.
error. You removed everything.
Then THR.
There's still a bit of blank left over there. You need to remove that before the bracket ends. Don't delete everything. Only the blank, please.
Uh, I'm removing everything, and when I'm retyping, it comes again.
No, see, you need to go to the right cursor. Can you go a bit right and then delete it first? Yeah, now type it, please. THR4. Now
Yeah.
go to the next blank and remove the blank first and then type. Remove the complete blank and then you can type total. There's still one part of the blank. Yeah. Now you can write total. 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 Okay. Now after the multiplication, you still have one blank. Can you remove that blank and write capital G?
Capital G. Yep.
Okay, Zain. Now we can go back to our code. And Zain, if you have any doubt, we will get a recording of the session also, so you can see over there also. Okay. Now we'll go forward. Okay. So if everyone has done this, can we run this code, please? Okay. Let's see what we are getting. What are we getting? Are we getting the sliders? Are we getting the sliders? Up over there. We are getting exhaust velocity slider, fuel fraction slider, and engine power slider, and a drag coefficient slider. Did we all get it? Now, experiment one. Can you drop VE to 1500 meter per second?
Three, 1,000.
1500. Yeah, almost 1500 also works. Yeah, great. That is the bottom of the slider. Now, with this, can a rocket achieve orbit? What will happen to delta V? So now experiment two. Now we'll push the fuel fraction to 0.93. Can we see the fuel fraction? We'll push it to 0.93, 0.93. Watch what happens at TWR. Can you see what is happening at TWR? Right. At some point, a structure stops existing because it is entirely fuel tank now. Okay. That means if you could only one change, do one change, only one parameter is supposed to change so that your rocket goes up exactly how you want it, what would be that? Will it be VE? Will it be fuel fraction? Will it be thrust? Or will it be CD? Which one will give the most improvement? Can we type it? I'll give the question in the chat box also so that we can. So if we could change after you saw that T or TWR is at 1.41 only right now. Now what is one? Why CD, Ismail? In Ahan, can you answer from what option that is given? VE, fuel fraction, thrust, or CD? Yeah, correct, Krish. That exhaust velocity. VE every single time because it is multiplying the entire equation that we wrote, right? Now, improving VE by even 10% improves the whole delta V by 10% everywhere across the entire flight. Now, fuel fraction improvement hits diminishing return because of the logarithm. This is why every generation of rocket is fundamentally about building better engine, not bigger fuel tank. We need to have better engines so that we use less fuel, but more power is there. Do we understand this? Can I get a reaction? Did we understand till here? We'll just quickly finish the rest of it. Okay, now for the next checkpoint, we have forces in flight. Again, your turn to code. Can we all do it faster? We have four blanks again. in the fill-in section, you can see rho equals to rho 0 into mathematical exponent. Remove the blank and you can write as minus altitude, not plus altitude. Add minus alt. And in the next blank, we'll add as capital H. That is the H scale. Okay. Now, why is this negative sign coming over here? And why do I need it? I said specifically to add negative sign. Negative sign is doing everything over here. It is making the density decrease as the altitude is increasing. Since we are coding it, since we are doing it mathematically over here, we need to say that it is decreasing as altitude is increasing. Otherwise, the whole point of rocket getting ahead won't work at all. Okay, for the next part, we are having gravitational acceleration, right? So here we could see G altitude equals to capital G multiplied by RE divided by RE plus altitude. So we'll write as ALT over there. And it is at the power of 2. Now we are having drag force. So what happens at the 400 kilometers altitude? Gravity is still 8.7 meters per second. It is not zero at all. Never zero. That means we never have zero gravity. Then why do we see ISS astronauts experience less gravity? They are in free fall. They are never in zero gravity. That is, they are falling every time in a near free fall situation. They are not having any contact force over there. So that is the reason they are always in a floating situation, not in zero gravity. So the next that we are having is drag force. Here we'll be adding rho in the blank and velocity in the next blank. That is, the drag force is half times rho times velocity squared times CD times area. Now, velocity squared, that is, the speed is double, and quadruple the drag. That is why max q is so dramatic at moderate altitude. Now, velocity must be in meter per second, not kilometers. So, if you accidentally use kilometer per second, drag will be 1 million times smaller than reality. Arav, if you have any question, you can please write in the chat, please. Your rocket will fly through the atmosphere now. If it is made of nothing, just like that, if we do this. So is it all done? We have one more gravity force over here. This should be remove the blank as mass multiplied by g altitude. That is mass times g at altitude. This is the simplest of the four that we did. Just do not use the surface value of capital G. We are using G underscore altitude that we just calculated. So please do not make sure that you have added your negative sign in the altitude initially. And can we now run it? And did we get another set of sliders? The next set, can we do the next checkpoint 6? Also, can we run it? Checkpoint 6. Now we'll be getting max Q, MECO, and SECO. Can we see it now? Are everyone able to see it? It's still running. We'll wait. Arav, what happened to you? Do you have any doubt, please? Can you tell me? Or you can just drop it in the chat, please. That would be better.
Yeah. Yeah. So can you hear me?
Yeah, I can hear you.
Yeah. So I dropped the doubt in the chat before, but like it seems you haven't seen it.
Miss
So like
for cell 5
you have
says T naught was not defined. Cell 5. Can you show me, please? Can you share your screen? What we can do is we'll get the a recording of the session after the whole session is over, and then you can see it over there. Did we get this chart right now? Okay. Now can we go to the next checkpoint, please? Here you we'll get an animation now. Can we use the animation here, please? Yeah. Can we run this? Just run it. There's no code that you have to do. Okay. Did everyone run it? And we'll play it now. Can we play it? It will take about 20 seconds to render, I guess. While it does, the play button is just at the right of the pause button. You can see the live graph and how the rocket is fueling up. You can see the stage one burning, you can see the stage two burning, and you can get the telemetry data just like you get in a webcast when you when we see any rocket launches. See, so when we ran it, at what altitude did the sky turn black? Can you tell me? You can see the sky changing colors. Can you tell me at which altitude? Either you can see all the altitude over there. Where was it that the sky turned from blue to black? You can see the live view over here where it shows altitude. Right now it is at 1031.5 kilometer. But when you started it, what was it? Can you run it again? See, it is now at 0 kilometers. So if we play it, okay. See, here around 80 kilometers is where it really starts to change colors. The official edge of our atmosphere or the space is 100 kilometers. That is called the Kármán line. But Rayleigh scattering disappears from about 80 onwards. So Rayleigh scattering is what makes our sky blue. And atmospheric molecules scatter shorter blue wavelengths repeatedly and preferentially. Now, above 80 kilometer, not enough molecules are there. So the sky goes black. So that is what we are seeing it over here. Now, we are having four movements over here, max Q. So we can see the HUD popped up there, that engine throttle back, the acceleration will dip slightly. Then we have MECO, that is the stage 2, T plus 162 seconds. And we can watch the flame. It goes from orange to blue, 9 Merlin engines off, 1 Merlin vacuum ignites. We all saw that in the animation. Then we also saw stars appear. Stars, there they are, around 80 kilometers, and Rayleigh scattering gone, exactly like we said. Correct? Did we all see that? Can I get a thumbs up from everyone? If we saw that. Okay, great. Now, did you also saw these orange dots that is happening over here? Those are the real SpaceX webcast telemetry data points, the actual data points that we are having the SpaceX we have in this code from an actual Falcon 9 launch. So our simulation built from physics equation that we wrote ourselves is tracking the real measured data. SECO, that is a T plus 572nd, engine is off, not because fuel ran off, because the mission is complete and the target was hit. Can you all tell me what surprised you most about this animation in the chat box, please? Just one thing. I don't need a lot of things. I just need one thing. Okay. Can you tell me what surprised you most about this animation? Ismail, Krish, can you all tell me, please? That we're able to make a simulation and get that? Okay. Great, Arav. Uh, the realism, the difference between values of velocity and other factors. Wow. Okay. So now we'll run the next cell and we'll screenshot the final two plots. These are your mission artifact from today. That is the final challenge. We are going to beat the real Falcon 9 over here. Okay, can we see is there a fill in the blanks over there? We did not fill it. Oops. So we'll go there and first fill it. So it should be my R equals 1 upon 1 minus my FF. My underscore FF. Okay, now we are having my dV equals to my VE. That is 2886 meter per second. These are all real parameters over here. Okay, and then we are having math log. In math log is my R. Math.log my R divided by 1000. My R has underscore, not a bracket. Okay, now we are having the next, that is my TWR, that is the thrust to weight ratio. Now, thrust to weight ratio is very important because if thrust to weight ratio is 1, it will be hovering over there, it won't move up. But if thrust to weight ratio is more, that means it can move up higher. And if it is less, that means gravity is more and it will pull it downwards. So here my TWR will be putting as my thrust, my underscore thrust, divided by m total into g. So we'll be multiplying capital G over here, not the small g. Remember to use capital G. Now everything is done. Now we'll run it again and see. Okay, what are we getting? Here. So now you can see there are orange dots. That are the real parameters. And the one that we are getting is the blue one. Now this slider is a challenge for you all to match at least a bit to the orange dots. You can use the sliders and you can see your graph will change downward. Oh, you did it too much. Okay, so this is a challenge for you guys that you can do. And now to complete the session, let's go down to the next cell and we'll get our mission report over here. These are your final two plots, the one that you guys used with the actual parameters, actual coding, the formulas, everything done by you guys. The physics that you use to produce these plots is the same physics that sized the propellant tanks of Hubble, Chandra, JWST, not a simplified version. It's all actual equations. So, in one sentence, what is an orbit? It is falling towards Earth while moving fast enough that Earth curves way beneath you. And it's always falling, but always missing. So it is moving like this, never going falling down. So that is the orbit, nothing more complicated than that. Now, JWST, I told you, could not use 10-meter mirror. It had to use only 6.5 meters. What stopped them? It should be Solkowski. If anyone ever asks you why did JWST never use 10 meters, you can answer as Solkowski. He is the reason we could not use 10-meter mirror. Every extra kilogram of the mirror weight that we would have put, that would have costed us about 40 to 50 kilograms of propellant to deliver it to the orbit. Now, if we use the logarithm scale over there, the Russian school teacher derived in 1903, working completely alone, before aircraft existed, is still the fundamental constraint. It won't deliver it properly. So now this is the end of our first session of launch mechanics. We completely got a mission report on how to launch our rocket. We built our rocket, we animated it, we got the simulation, a realistic simulation and everything. So now this session, now we have a next session coming, that is reading the sky. Now we saw that observatory is in orbit, that is telescopes are all there in the flight, in the space. So next session, we use what it carries, the real stellar data downloaded from actual astronomical databases, and we'll be using that, understanding the spectral type exactly the way professional astronomers do it. Now we'll be using the same energy, probably the same code, but we'll be using a different universe. So Now, a post-session form would be available for you. Just like we did a pre-session form, a post-session form will be available for you in the LOF app. And I all want you to get into the LOF app, into the LOF community, so you can get more data of it and get the recording of the session also over there. So whoever was not able to code or was stuck at somewhere, they can see the recording and get it done very easily. So now Shrishti will be explaining you how to get into LOF community, and that would help us to get into more such sessions. So over to you, Shrishti, now.
I'm sorry, you guys can hear me now?
Yes, we can hear you now.
Thank you everyone for joining today's masterclass. You all did a fantastic and a wonderful job. I just love the energy that you had today. So this is just the beginning. Let me just show you. You guys can see the screen?
Yes, we can see the screen, Shrishti.
Great. So as I was saying, remember, this is just a starting step. So what is it? What is that? Every day we conduct a lot of activities for you guys. So what happens in this activity is there where you get your space credit. So what is space credit, if you ask me? It is more like and how do I say this? More like a reward for your learnings, whatever you do. So here, right now, by attending this session, you have got almost 100 credit for you guys. The more the missions and activities that you do in our app is more space credit that you get. So before that, I just want to know how many of you are from Jaipur or Dubai? Can you just type down where you're from? Okay. So Dubai, we are starting our camps in the month of July, and in Jaipur, where you learn. Just let me show the video. This is the place where students will learn about the flying inside the wind tunnel, about the anti-gravity. A lot of things are happening. So you guys can get up there. And what I want you guys to do it is join our community by scanning the code. By maybe Android users, you can scan the Android code, and iOS users, you can scan this and you can get into our community. And to get your certificate, please do message us in our community at labofuture.com with your full name so that your participation certificate will be given there. So guys, any doubts? Anything? No. Okay. Great then. I hope to see you there.
Did you all enjoy the session today? Can I get a reaction for that? How was the session? You can type in the chat box also. Okay, are you excited for the next session? To
Also,
understand more
guys,
about stars, to more about how we get near to the stars. Okay, so I hope I see you in the next session.
yes. Also, guys, we are conducting a robotics webinar as well. I want everyone to, join us there. You can scan the QR code here and you can register yourself for that as well. Remember, the more activities, the more quiz that you conduct, the more activities that you do it, you will get more space credit. It means more on the leaderboard. Okay? Okay, guys. It was a nice session. Thank you, Smriti, for conducting such a good session. And students, you are great. Okay?
Thank you so much.
Thank you, guys. Thank you so much. Hope to see you soon.
Yes, Zaim, you can please spam us in the LOF app so that we can reply back to you. Right now, the time is almost over, so we'll get back to you in the LOF app. Make sure you download the app and get into it and let us know how you felt about the session too. Okay, bye bye.
Also, you guys can answer all the, you can drop your questions in the community at laboffuture.com. So
Yes,
we personally answer them. Okay.
and make sure you do the quiz of this session so that I know how much of you understood that. Okay, bye.
Bye, guys.